Anything where sacrifice. Mhm. Basically, if we come in and give you a scenario, let's say we have this reading here and this reading here, what would be the most likely cause, or what would be the components that might cause that problem? That's looking for. Full ways for this, right? This is where it's coming out of. You won't have an oscilloscope, right? What's your main troubleshooting tool? Your meter. But before you start troubleshooting, you got to understand how this thing works, right? You understand? If you don't know how this thing works, if you don't know what you expect to measure with a meter, then don't put your meter in a circuit, right? So it's very unsafe to put a meter in a circuit to see what's there. What we need to do is put a meter in a circuit to verify what we expect to be there, right? It's not what we expect to be there. It doesn't necessarily mean it's wrong, but you might have anticipated wrong, right? But power supply is pretty given what you expect out for what you put in, right? You understand that? So we know the makeup of the power supply just basically consists of this linear power supply just basically consists of sort of that I got on my computer, which I thought I did. So at that point, so if we look at the power supplies on the trainer, we would first of all we need to be able to identify the sections because here this is a block diagram, but what you've got an actual schematic, right? You understand that? So this is what they're talking about here. So of course, the capacitor filter would be hard to do this, but we have different ways we can filter the power supply. The most popular method is with a capacitor filter. Another filter we have is what we call inductive filter. So with the capacitor filter, it's pretty easy to see because what we'll do is we'll just put, uh, so we have the output, we have our pulsating DC, right? And then we come over here and we have a capacitor, and then this is gone and it converts it into this unregulated system. What can go wrong with the capacitor? And what would you expect if the capacitor was bad? And then we feed this into our watt. And we might have multiple regulators. Then we feed this into our regulator. And sometimes we have some pre and post right here, but these capacitors are not real big. This is to filter out the noise that the regulator generates. So the regulator is constantly trying to do what? Maintain an output, and it can literally generate noise itself. So normally we have a pre-filter and a post-filter, but these are small. I think the 7800 series recommends the 1 microfarad there. And over here, I think they recommend like a 10 microfarad. This guy over here is going to be thousands of microfarads. So I think one of the ones the trainer uses a 2,200 microfarad capacitor. So this is the main guy. But what would happen if one of these, what could go bad with the capacitor? So we got two things that can happen to electronic components. We know two of them. What's the two things that happens to most electronic devices? Uh, yeah, but I'm talking about what causes it. I'm talking about the results of the cause is what I'm talking about here. Right? You understand? So yeah, they get hot. If they get too hot, it's going to cause something else to happen. They're either going to open or they're going to short. Now, the third thing we have with capacitors is they could become leaky. So what would happen if the capacitor shorts? What would we expect to see on our output with a meter if the capacitor opens? I don't know. So what I'm doing, I'm turning DC to pulsating DC, unregulated DC, right? Minus D ripple DC divided by 2. Pulsating DC depends on halfway. Equal to B peak over pi. So here I'm dividing by 3.14 over other. I'm just subtracting out 1/2 of the ripple voltage. So if that capacitor opens, what's going to happen to my DC output? Is it going to go be a lot higher than it was supposed to be, or it's supposed to be a lot lower than it's supposed to be? Lower out. And I come in here with the meter, I measure this, it's real low. I come over here and measure this, it's real low. Then it's not the regulator. The regulator just can't regulate what it's got, right? You understand? So to regulate, what does the regulator have to have on this side over here on the left-hand side? More or less than the output? Huh? Does it have to have more? Or you can't agree because I'm asking two questions. Is it going to be more? If it's going to regulate, does it have to have more DC on the unregulated side or less DC? It's got to have more, right? You understand? So if I'm getting 5 volts out, I'm supposed to get 5 volts out, and it's measuring 3 volts, and I come on my other side over there, and it's only got 3 or 2 volts in. Then it's not the regulator's fault, right? You understand? It's what we could have a bad diode, but a bad diode won't affect it near as much because it's still right here. It's still half wave or full wave, right? You understand? It's just that it won't be as high as it's supposed to be. If it's extremely low, then you got 1 or 2 problems, guys. You either got a bad diode, you either got a bad capacitor, you got a bad. Understand? Well, what if you measure 0 on the output and 0 on the input? Could be the fuse. Well, what would I do to check that? Well, maybe not. I got my meter in there, right? How would you check a fuse? So here's my fuse. The trainer doesn't do this. We put it right here, right? Okay, that's the wrong symbol for a fuse. So we would put our overcurrent protection device where? Right here, right? Understand that. So how do you check a fuse if you don't pull it out of if you don't pull it out? Well, or a wire. So you got your fuse, right? It's going to be right here. Very few power supplies use circuit breakers. Because why? I've never seen a power supply use a circuit breaker. Cost, yeah. That's the reason. Right, you understand? So what I would do is somewhere how would I check a fuse with a voltmeter? With power on, because that's why we're troubleshooting right now. How would we do that? So what should I measure? Well, we could measure across it. We don't like to measure across things in the circuit. Why is that? I can avoid this. I avoid this. I can possibly do. Unfortunately, we don't teach this in DC. I got these two metal rods probed inside a circuit, right? I'm trying to look at my meter with two things inside a circuit. It's very close to each other. Okay. What do we do when we normally troubleshoot? We take this sucker right here and we get an alligator clip and we clip it onto our common and troubleshoot relative to this, right? Which works out better because now I've only got one hand in the circuit. Number one, I've only got one hand in the circuit and I'm sticking out here, right? You understand? Now, most of your meters come in here now and they have a cap that comes over here and tries to cover this up and avoid that. But you're going to see people taking things off all the time because it's right, which is not good. Yes. So now I'm going to measure this relative common. So how much voltage should AC drop if it's good? 0. Yeah. So what that means is, as I should measure the same thing on this side that I measure on that side. So if I measure 0 on both sides, you got a big problem. Alkaline power's got a problem, right? If I measure 0 on my output side and 120 or whatever volts on the input side, it means the fuse is blown. If I measure it on the side, then what does that mean? That means it's good. The fuse is good. If you measure the same thing on what? Both sides. Everybody understand that? So you can check the fuse. But what if the fuse is good? Check the output of the transformer, yeah. So we come here and we do what? We measure the output of the transformer. So you need to know what that's supposed to measure. Of course, your meter is going to measure RMS. So we got 0 here, we got 0 here. We come over here and we measure this. If it measures 0 right there, and then I have on my primary, I measure something, and what's the problem? So we got 0 here, we have AC over here, we have 0 there. Then the problem with it is what? Right? If I've got AC right here, and then I measure 0 right here, what does that mean? Could be the rectifier, could be the filter. Right? Well, odds are it depends on what type of filter it is. So a capacitive filter, we put the filters like this. Inductive sensor. So inductors and capacitors are exactly opposite. So if they're exactly opposite of each other, then just if you use capacitors in a power supply, you're going to put them in parallel. If you do the inductors, you're going to put them in series. So capacitors charge and discharge electrostatically. Inductors charge and discharge magnetically. So if I've got something that changes real fast, my inductor hates that. It'll block that. So all that pulse in DC is going to do what? It's going to block it. So it'll do the same thing. But the problem is that the filter is an inductive filter, and you measure 0 volts right here, and you measure something right there, it means your filter is bad, right? You understand that? Capacitors, if you measure 0 right here and 0 right there, it's probably not your capacitor because your capacitor can short, but if your capacitor short circuits, then what's going to happen? It's going to blow a fuse, right? Hopefully. Our trainers don't do that. Our trainers burn up the transformer because its fuse is too big. So we're working on our work studies, working on the trainers that's not working. So on one of ours, this guy right here is blown up. Could be capacitors. The problem is, if capacitors short, they could blow up. But this is usually what causes them to go bad when they come leaky. When they come leaky, so a capacitor technically there's no current that passes through it. Since there's no current that passes through it, the current flows in and out of it, right? You understand there's no current that passes through it. It does no electrical work. It does no watts. So capacitor is not supposed to get hot, hotter than the ambient temperature. If you got a capacitor that's getting hot, then it's bad, right? You understand that? Well, what happens if current flow starts flowing through it? Now we got P is equal to I square R, or P is equal to I times V, right? You understand? So now the capacitor just gets hotter and hotter. It's got nowhere to go. So what will it do? It'll expand up, and then it'll pop. We showed you all that video, right? Yeah. So we got one in our trainer that's done the same thing. So, huh? Yeah, the top actually popped off. We found the top inside the trainer, and it actually popped off. I mean, so it's still intact. So we was able to read it and get the size on it, but we didn't really need that because we got the schematic. So one of our trainers is done like that. So what could cause it to do like that? Well, we could exceed the working voltage, right? You understand that? So something went wrong and exceeded the working voltage, or the capacitor became leaky. And when it becomes leaky, now all of a sudden you're putting current through a voltage. Anytime you put current through the voltage, you create power. It acts like heat. Those things are sealed up, right? You understand? And what does heat cause air to do? To expand, and it's to go, and eventually it'll either and that's why we so this is basically what we're talking about. And y'all look function of each one of these units, right? So that's just what could the probable cause of a low output. What could be the probable cause of an output that's higher than what it's supposed to be? There's only one component because it would be higher. The regulator, yes. The regulator shorted. So what it's doing is letting our unregulated come through, so it's shorted. So regulators can do the same thing. They can short, or they can open, or they can become leaky. They can become leaky. It's control of the regulator. It's not doing its job, right? So this is the problem we have with solid-state devices. They can go three different ways. They can do what? Open, short, or become leaky. So resistors are either going to open or resistors are a little different in that they either open or the resistance goes up. I've never seen a resistor short. I've seen resistors be shorted around. Somebody screws up and shorts around the resistor, like with a meter. Right? They're trying to measure across the resistor, and then they short the resistor out, and that causes big problems because that's called what we call a cascade effect. What y'all think? Y'all could be able to do this okay? And we'll do it relative to a meter and not relative to a scope. You might be lucky enough to get a scope where you work at. But, yeah, this is. This is the basic drawing, right? Y'all understand the troubleshoot a power supply. Because all of them's the same. I mean, the only thing that the filter does not specify is what type of filter we have. Sometimes we have L filters, which are, what advantage does a capacitor filter have over an inductor filter? There's only one, guys. No. Because capacitors are a lot cheaper. Inductors are made of copper wire. Copper wire costs money, right? You understand? Capacitors usually use lead and tin. The big electrolytic capacitors, because to get rid of electrons, so that's why they're polarized. So in these capacitors, they're going to be electrolytic capacitors. And they just use two metals that's wrapped around each other, right? And they're not very expensive metals. And type of insulator. Y'all seen one? I'll go get the one that's blown up and show y'all. It's just two flat rolls of metal, right? Right, and it uses a paper, between, and then on one end, that's what. So literally, that's all this electrolytic capacitor. I'll just draw one. They'll come up here and connect one. They'll come this way, and then they'll come over and connect this one, and they'll go this way. I'm just doing one route. And what do they put in between them? They put an insulator. That's all it is, and it's usually a paper coated device. Understand that? And then they can change the size of the plate by putting more rolls, right? Bigger this way. So the more rolls they put, the bigger the radius, the hammer goes. The bigger they make the plates this way, the taller they get, and it's all part of the design when they design these electrolytic capacitors. So anything else on there? Yeah, so this came out. This didn't come out of y'all's book. I don't have a copy. I don't have the PowerPoints for y'all's book, but I think the one in the and I think the small book didn't have that in there. These are with this is with silicon. I don't know what you got here. This is a halfway rectifier. There's no going from a half wave over to a full wave or vice versa. Full wave, if we lose one of the diodes, it turns it into a half wave. Well, the half wave can only go on. If it opens, then what? We'll get zero on the output. Now, zero on the output. And the problem we have with AC, guys, is anytime we get an open in AC will couple through just about anything. If we get an open, we're basically forming a capacitor, right? We got a wire over here, we got a wire over there, and we get an open. AC will couple through anything. The problem we have with an oscilloscope is that this oscilloscope goes down to 20 millivolts per division. So there's a 99% chance of you turning that oscilloscope down far enough, you're going to see something. You're going to see some form of AC, right? You understand that? I can do that just by turning the oscilloscope on, right? You understand that? And we have people that don't understand that zero would only occur if you're see what something. We get this big problem with we teach level computer troubleshooting class, and digital pulses. And you would see people, they would turn the oscilloscope down until they saw something, and they said it was good. Pulses over here, we had 20 millivolt pulses, and they said it was good because it was coupling through the open, right? You understand that? When I see this zero right here on this side right there, does that necessarily mean the diode's open? What's the next place I would get? So here they say it's open, but I wouldn't stay there. If I saw zero on the output, what would I do next? I'd check the transformer. I move it over to the transformer, right? So if you got nothing on the cathode of the diode, and you've got nothing on the cathode of the diode, you don't know if the diode's good or bad, but you know the transformer's definitely got a problem. And then you would check the fuse, right? Let me show you what they did on the trainer power supply. This is causing a couple of problems. What they did is, I don't know. Here's the neon bulb right here, and notice where it's at. On it, like if I was to blow the fuse on the power supply, the on-off, which is not going to light up. Here, though, when we close the switch, notice the neon bulb is before the fuse. So I mean, if the fuse blows, then you flip the light will blow, which has caused me several problems. Because, I think the fuse is good, but when I look at the schematic, I said, no, I don't want to. Normally, every part of the power system supply should be on the fuse side, right? You understand that? What's something go wrong here? Something could go wrong with it. But here's the fuse. And they're using the similar fuse. No. Most people say, well, if I've got 5 amps over here, I need a 5 amp fuse over there. But this is at 5 volts. That's 25 watts worth of power, right? So 5 volts, 5 amps is 25 watts worth of power. If I put a 5 amps there on the 120 volt side, that was 600 watts of power. That would be through, right? You understand? So people don't understand the difference between the primary fuse and how much the power supply delivers. The primary is giving us the power at a lot higher voltage, right? You understand? Right? You understand that? So this gets people confused. I've seen people do that. They got an 8 amp power supply and they think, by George, they got to do what? They got to use an 8 amp fuse on the primary. So that 5 volt supply, 25 watts. So if I just use the 5 volt supply, then I would say 120, right? I'd say 25 divided by 120. And then I would increase it by 150%. It depends on the power supply. 5 volts, they would probably use it at 200%. So what I use for a 5 amp 5 volt supply. Here's 25 watts of power I need over here, right? Right? 200%. Double it. So 25 divided by 5. I is equal to P over V, right? 25, divided by 120, right? Okay, and then we multiply Q times 2, and we go up to the next standard value. Because they don't make fuses in infinite values. They got standard values of fuses too, right? So what size fuse? What do we calculate? 416 milliamps, right? Right. So that's so much smaller because it's delivering at watt. Power is power. Use the same size fuse. Power supply changes two things. procedure for calculating the primary Q's on a power supply. Any more questions? I think that's on the test, I think. 237. Rich and light with a straight face, zero. I don't know. It's got a handout section. It's on there. It's got a just like before section that you do work, right? And then it's got a multiple choice. A power supply. Right. One of those circuits on there, only one. I'll tell you which one. I got two circuits on there. One's a singer for sure. And then the other circuit came off one of the other tests. So there's two circuits on this test. Huh? I thought I did. It should be up there. If it's not, it's not up there. And the key's on there too, right? And the test reviews up there, right? I know it went on there Sunday. Okay, I'll put it up there. I've got the test review right there. It'll be up there for Anthony. It should be. It's not. Well, do the worksheet. Y'all need to try to remind me to go up there and make not only the sheet, but also the key to the worksheet. Oh, Joe, Justin, I was trying to remember who else is on here. And I don't know what's going on. I know Anthony is off at like 7 or 8 works swing shift. A lot of people do it forward. It's just, a commitment that you have to make. Blackboard's been so slow lately. Blackboard's fine. So we're down this weekend. So the internodes, worksheets. Well, it's not available. So every time we do a worksheet and I come in, I